about AdS3 RMT2 duality. Over to you, Eric.
Thank you very much, and thanks for the invitation to give a talk about this topic. I am going to talk about some work that's mostly based on a paper that came out last summer, and originally I was slated to give this seminar a few months ago, but due to various logistical things, it got postponed. But the original, I think, intention was to hear about this work, and it's still something I'm very actively working on, and some follow-ups to it. So it is based on work with my student, Gabriele Di Ubaldo, and we're joining forces with some others as well. I'll mention that in due time. So the main question that this work aims to address is there an RMT for CFT? So to put this, a few more words on that, conformal field theories are not theories of random matrices, but they are expected to have rich dynamics, and we want to understand a framework which marries the random matrix dynamics we expect of high-energy states in CFTs with the constraints of CFTs. Part of the motivation comes from thinking about AdS-CFT, where in the low-dimensional context, we have the duality between JT gravity and ensemble of random matrices. As we are all likely familiar with, this duality involves wormholes on the gravity side, space-time wormholes which connect multiple asymptotic regions. But there's no factorization problem because the boundary theory involves an explicit averaging over an ensemble of matrices. But this raises questions for higher dimensional holography. These are not original questions. The way I would put the two main questions are as follows. First, traditional AdS-CFT works. How do we interpret space-time wormholes from the CFT point of view then? And second, in more than two bulk dimensions, black hole microstates should in some appropriate sense exhibit random matrix statistics, as was nicely shown in this work by Cotler et al. From 7 or 8 years ago. But in what sense should these statistics be present in the spectrum of black hole microstates? And from the boundary point of view, in a CFT in 2 or more dimensions, how do we find these random matrices? So today I'll focus on AdS3 CFT2, one dimension up from the JT-RMT story, which is rich enough and has enough technical advantages that one can actually make progress, as is often the case for 2D CFTs. A consistent 2D CFT exhibits locality and obeys certain bootstrap and symmetry constraints, the main ones being Virasoro symmetry of the theory, namely all of the local operators organize themselves into representations of the Virasoro algebra, and the SL2Z covariance of local observables on the torus, most notably the invariance of the torus partition function. Now, in the bootstrap point of view of CFTs, we're used to asking the question of how the heavy spectrum, the spectrum of high energy states, is constrained. But we usually end up asking this question, or at least answering it, on average, in the sense that things like the Carty formula really apply in some asymptotic regime in which, to make those statements precise, one needs to average over a window of energies. This was nicely studied in a more rigorous way in a paper by Mukhamedsanov and Zhivoidov from a few years back. But a newer, more refined question is to ask how the bootstrap constrains heavy spectral correlations between individual energy eigenstates. Whereas this old question is the purview of the Carty formula, various asymptotic expansions, properties of modular kernels, that is, the crossing kernel for individual states in some other channel. The new question is really where chaos and random matrices ought to live. So today, I'll present a framework for random matrix dynamics in 2D CFT, which I think has a lot more to teach us than what I'll actually say today. It's built on a trace formula for 2D CFT Virasoro primary spectra, which applies to all actual 2D CFTs. It's not a model. And it arises from a new way to think about modular invariance, which points us toward a nice definition for what the chaotic spectrum is of a 2D CFT, which is a question which, if you think about it, has sort of defied a sharp characterization, and I'll give a characterization. Now, when we apply this to AdS3 pure gravity, this gives a microscopic explanation, in fact, and allows us to factorize the Cotler-Jensen wormhole to extract a new contribution to the high energy spectrum of black holes in AdS3 gravity. Here I've given a sort of sketch of what I mean. So the gravity partition function of the torus is given by the sum over BTZ black holes, a la Maloney, Witten, Keller. And now there's a new additive piece which we are determining from this computation, which I'll spell out in due time. Okay, to be clear, I'm not claiming to have solved the problem of pure gravity. This is a contribution, which is quantum, but not the full story. Okay, so I'm not quite done with the introduction. So there's going to be a 0th part to the talk, which is to talk a bit more about the AdS3 pure gravity problem as motivation for this 2D CFT framework. And hopefully this won't just be me talking. Feel free to interrupt with questions. And I just want to start with some perspective on the current state of the art in the world of AdS3 CFT2. And then we'll transition to introducing the trace formula and a notion of random matrix universality for 2D CFTs, which leads us to a kind of conjecture, which is based on some work in progress. Then we'll turn to the AdS3 story and the Cotler-Jensen wormhole and the black holes in AdS3 gravity. Okay. Good. So first, the sort of setting the stage. So let us recall what I'll call the AdS3 pure gravity problem, namely its simplest version, the one that's been studied for about 15, 20 years, which is to find a consistent semi-classical AdS3 pure gravity partition function with a single torus boundary. So no wormholes, no higher topology, just what is the spectrum of states of a theory of pure gravity? Can it be made consistent? That is, unitary in particular. Now, the original proposal for how to do this was given by Maloney and Witten, then refined by Keller and Maloney. It's very natural. You sum over smooth saddles with torus boundary conditions. So you're just summing over all the smooth saddle points and the fluctuations around each saddle point. This is given, this full set of such smooth saddles is given by empty ADS and all the BTZ black holes related by SL2Z images. Now, this calculation, famously, is non-unitary. It's actually highly, that is, exponentially non-unitary. There's a window near extremality where there's an infinite, exponentially large number of negative degeneracies. It's a small window, but it's a large degeneracy. So to me, this is a large problem. So how do we fix this? Well, here I've written plus z off shell because, well, we've already summed over all of the on-shell stuff and fluctuations of gravitons around that. And so we want to solve the problem without adding non-gravitational degrees of freedom, that is matter, states with dimensions below the classical black hole threshold. And so the only option is to add something else, which I'm just calling z off shell because they're not solutions and they're not matter. So what else can it be? And indeed, we know from other contexts that we should now be taking off-shell contributions to gravitational partition functions more seriously, hence the name.
I have a question.
Yes, please.
So why do you expect that the sum over smooth saddles would give rise to the exact answer? Because it's, after all, an approximation, right?
Yes. So in the large C limit, that's a reasonable expectation. Yeah. So I think when their calculation was first done, it can be done holding C fixed and finite. And then there was some objection that the resulting spectrum, well, that was before the major negativity was discovered. The resulting spectrum was continuous, and this was seen as a problem. In fact, this isn't really a problem because you should view it as a large C limit. And then in a theory where you expect exponentially small spacings between states, those would close to zero unless you're sensitive to exponentially small corrections. So one could have plausibly hoped that that calculation gave you a good answer to, perturbatively in a small G Newton expansion.
Okay.
All right. So good. So this is the thing we want to construct. We want to find a unitary such combination of the sum of our saddles plus something, which in the bulk should be some off-shell contributions. And we should ask ourselves how the answer might be informed by JT-RMT duality, which is the duality that in some sense we now understand best, at least for the kinds of questions I'm posing here. So let's examine this relation a little bit more and ask ourselves what question we should be asking ourselves. So on the right-hand side of this duality is a random matrix ensemble. And to me, there are two pieces to that phrase, random matrix and ensemble. Now, there's been a lot of work recently in AdS3 understanding the ensemble aspect of holographic duality. Starting from a paper a couple of years ago by Chandra et al., it was shown that if you study an arbitrary wormhole saddle with arbitrary fixed topology and perhaps some conical defect states running between the boundaries, that this saddle point partition function can be computed by doing what looks like an ensemble calculation in CFT. There's what they call the large C ensemble of CFT data. That is some sort of statistical distribution of a density of states and OP coefficients. And you can compute moments of these distributions, and that gives you the saddle point partition functions to all orders in the 1/C expansion. This story has since been improved upon and sort of corrected in a paper by Bellin et al., who realized there were some non-Gaussian corrections that are not small to this putative ensemble that one needs to get the bulk answers right. Another recent perspective has been given by this so-called Virasoro TQFT, which is a prescription to compute these saddle point partition functions for any hyperbolic three manifold, where the word hyperbolic is doing the work of saying this is an on-shell bulk saddle. Now, this ensemble, these calculations, is fixed by the vacuum plus crossing. So to construct, for example, the density of states in the ensemble, it's just the Cardy formula. And one gets that by taking the identity in one channel and branching it under an S modular transformation into the other channel. So this is like the leading piece of the Cardy formula. And that formed the density of states for this ensemble. Likewise for the OP coefficients. And so for this reason, it's probing universality of CFT data at large energies. That is the sort of ETH structure of theories at large energies, but not the chaos, that is to say, the fine structure of the high energy states. This ensemble is not related to random matrix statistics. It's fair to say, I think, that it's also still a bit unclear what to make of the ensemble point of view, aside from being a way to reproduce gravitational answers. There's clearly some sense in which gravity is computing some quantities which are coarse-grained or smoothed out. And what we need to explain, as articulated by Schlenker and Witten, is why gravity gives apparent averaged quantities, not so much why holography is inherently some averaged thing. Even in the semi-classical limit, it's not clear that one needs to invoke ensembles as opposed to just properties of large C limits where you kick out exponentially small terms. So for these reasons, the ensemble studies of AdS3 gravity are not quite capturing data about the black hole spectrum at the microscopic level. That, of course, is living in the random matrix part of this phrase. In any CFT in any number of dimensions, random matrix dynamics should govern the high energy spectrum. And indeed, this seems to lie at the heart of the pure gravity problem in AdS3, I would argue. When we ask, how do we unitarize the naive semi-classical black hole spectrum? This seems to be the same question or at least intimately related to the question, how are random matrices encoded in the edge of the spectrum near extremality? A very nice paper by Maxfield and Teriachi gave a sort of implicit proposal for how to fix this negativity of this Maloney-Witten partition function, which involved a dimensional reduction to JT gravity plus defects and understanding the random, recasting the calculation as a sum over defect states in AdS2 as a calculation of random matrix theory. And their proposal is implicit from the 3D point of view, but gives a sort of definite sort of homework assignment for us for what we should be doing in AdS3, which is to understand how random matrix dynamics of AdS3 black hole states near extremality end up unitarizing the negativity that the naive sum gives. And so for all these reasons, I would conjecture, this is a joke, of course, that we should understand random matrix dynamics in AdS3 CFT2. I think it's a very important problem. Let me pause and ask if there are any questions, because here I'm articulating my view on the state of the art, and different people have different perspectives. And, I think the lesson that I'm trying to say is that all the work on ensembles is not really capable of touching on these questions about the black hole microstates.
So I have a question.
Yes.
So do you expect that the conformal field theory correlators, when the correlation functions are kind of expanded in a Cullen-Lehman representation, the spectral decomposition of the correlator, what do you expect for the density of, the spectral density, rho of Q square, which sits in the Cullen-Lehman representation? Do you expect it to be the Wigner semicircle or something?
Some generalization of that, which is partly, not one needs to embed that statement into CFT somehow, right? You need to find the version of that statement that is compatible with the symmetries of the problem and the organization of the spectrum into representations of, say, Virasoro and so on. But yeah, some version of that at high energies should hold. That's what I would say.
Thanks.
Sure.
Sudhir has a question. You can go ahead.
Yes.
Yeah, okay. Can you hear me?
Yes.
So the CFT2, there should be a black hole threshold, right? So what do you mean by the edge of the spectrum? Are you saying that you're going to use random matrix theory even below the black hole threshold?
No. So you're right that when I say will be above would be black hole threshold. So in CFT language, that at large C, that would be C over 12. There should be corrections to this. But yeah, when I say edge of the spectrum, I mean where the left moving dimension is, say, approaching C over 24, and the right moving dimension, is going off to infinity if you have some large spin near extreme black hole. Then
okay.
that
And
was the
my
regime
other
where,
question was, in some of these earlier papers, they talk about approximate CFTs.
yes.
You're not referring to that. You believe there are exact solutions of the crossing equations, and you're just looking at average properties of those exact solutions.
Yes. So I think I'm not sure the notion of approximate CFT is needed to explain what gravity is telling us, but I actually don't strongly object to the philosophy of that paper. I think it makes sense to talk about satisfying crossing with some small tolerance. But I think that approach might end up in the large C limit being equivalent to a different, more microscopic approach.
Okay, yeah, no, I also had a little trouble understanding what they were trying to do. Okay, thank you.
Okay. So with this kind of motivation, Cotler and Jensen computed the two-boundary torus wormhole of pure AdS3 gravity. This is not a saddle point. It's not a hyperbolic manifold unless you have some defect state running in between. But if you're just computing this apparently two-point spectral correlation, then it's not a saddle point. So they had to use some unfamiliar techniques involving constrained instantons and the like. But the answer is very nice. It indicates something like spectral level repulsion, which they playfully called random CFT. And it looks, if you go to the microcanonical ensemble, look at the sort of energy correlation. It looks like a 2-point correlation of some chaotic density of states, which obeys some random matrix statistics. But there's some imprecision or just mystery, really, about this calculation, how to interpret it. So first of all, what exactly is being correlated on the boundaries? In this interpretation, what are these brackets supposed to mean? Is this a microscopic calculation? Is it an average calculation? How is the average done? What is going on? And just, as an overarching comment, what does random CFT mean? What is this really supposed to mean? In a nuts and bolts way. Okay, so that's the invitation from pure gravity. Now we'll talk about the CFT and then go back to gravity later. All right, so the first question we want to answer is, what is the chaotic part of a 2D CFT spectrum? There's no immediately obvious precise definition, especially at finite central charge. At a large central charge, you might think it's the energies above which black holes exist, but the exact location of the threshold is not totally clear. But at finite C, especially, one doesn't really know where the chaos starts, or whether that's a sharp question to even ask. But holography suggests an answer, and this answer ought to respect modular invariance of the torus partition function, which is an exact symmetry of the theory. We know that for some given low energy states, modular invariance ends up relating them to some part of the high energy density of states. But actually, there's some more information in the high energy density of states than that, and that's kind of where I'll argue the chaos is sitting. Formally speaking, as we showed in this paper from 2021, if you take the primary partition function of a Virasoro CFT with C greater than 1, so by primary, I mean you take Z, you strip off the descendants by multiplying by this modular invariant prefactor, which gets rid of the eta functions. And throughout the talk, I'll be using this notation for tau, x plus I, y. And I guess sometimes I'll use this here. We can take the partition function, we can write it as a sum of two pieces. Both pieces are SL2Z invariant, but they're a very different nature. Okay, so for this slide, I'm calling them Z smooth plus Z chaotic, just to give away the punchline. So what is Z smooth? You take your light states, so take all states where the minimum of the left and right moving dimensions is bounded above by C minus 1 over 24. And we sum over those states. And then we take the SL2Z sum over images of those states. That makes an SL2Z invariant object. It's the modular completion, if you like, of the light spectrum. Now, when you do this in an irrational CFT, for a given character, the modular completion doesn't add any more light states. It only adds heavy states. So you have a bunch of light states, and now you have some new contribution to the heavy spectrum from this modular completion, but you've made something which is modular invariant out of just the light states. So that's what Z smooth is. And to this we add what I call Z chaotic. That's just what's left. Okay, but you can think of it as the actual heavy spectrum minus all the funny heavy stuff that you added from over here. Okay, but this being modular invariant and this being modular invariant means that this too is modular invariant. And this Z chaotic piece has support only on heavy states. This, of course, is the black hole regime in gravity, but it's telling us something more generally, even at finite C. Okay, so originally when we proposed this, we used a different notation because we're not trying to cheat. Let's call Z smooth Z hat light, right? So it's the light piece plus the modular completion. That is all the sort of continuum of heavy states that you get by insisting on SL2Z invariance. And Z spec is what is left. Okay. The reason for that notation will become clear in a second. So again, morally, Z hat light is low energy data plus some high energy data, which just comes from modular invariance. Now, you can do this decomposition in Narain CFT as well, which we did in the original paper. And you can show that if you average over the Narain moduli space, which I've just sort of playfully pictured here as this teardrop, then this extra Z spec part, averaged over the moduli M, actually vanishes. So averaging over the full space of an array in CFTs at some fixed C just lands you back on this piece here. So in that sense, this Z hat light piece is self-averaging in the array. And it suggests that even in a generic Virasoro CFT, this Z spec is containing chaotic fluctuations, the part of the spectrum that restores discreteness and the would-be chaos of the actual high-energy spectrum. And so we want to seek a sense in which we can show that indeed this Z spec is chaotic. Let's state this again with a picture and slightly different language. If we look at the density of states itself, not the partition function, that's a sector of fixed spin J. That likewise splits into this piece, rho hat light plus rho spec. Now, if the thing on the left is the exact density, in a compact theory, this is the sum of delta functions. Here I'm just approximating it as this smooth curve, right? But think of this really as a sum of a bunch of delta functions. Then rho hat light is this continuous exponential asymptotic, which comes from completing these light states. So here I've just pictured the heavy part of the spectrum with T greater than 0. And so in the heavy spectrum, you have the actual heavy spectrum given by the solid line, approximated as a smooth curve. And the dotted line is the piece coming from the completion of the light states, which is like the Carty formula. It's the smooth, high-energy piece which comes from modular invariance of the low-energy stuff. And so what's left is rho spec, the green parts, the little bits in between. And you see that if rho is discrete, rho hat light is, in general, not discrete. It's continuous. And so this rho spec must oscillate on scales, e to the minus Carty, roughly speaking, in order to restore the discreteness of the actual density of states. So this rho spec is highly oscillatory and, small and wiggly. This hints at some analogy with the Guthwiller trace formula for quantum systems. So let's recall that briefly. If you have a spectral density rho, you can split it into some mean density rho bar and what's sometimes called the oscillatory piece of the density, rho os. And the oscillatory term can be recast as a sum over semi-classical periodic orbits of the system. I'm indexing the sum by some gamma. There's some e to the I action, a period, prefactor given by the derivative of the action, and then some one-loop determinant piece here, often written as A gamma. Okay. And this 1 over pi is just a convention. So gamma runs over the semi-classical periodic orbits of some system with some fixed Hamiltonian. And the suggested analogy, which perhaps is clear, is that rho bar is like rho hat light, and this oscillatory density is analogous to rho spec. Okay, so on the right-hand side, these are 2D CFT quantities, and these are the quantities in the, the quantum system where this is given by the Guthwiller trace formula. So we can make this analogy sharp, and that really is the first punchline. Okay. So where does this proposal come from? It turns out, in a slightly, maybe something surprising and nice, that insisting on SL2Z invariance is what gets us this. So by construction, this thing I called Z spec it's modular invariant, but it's also square integrable, because recall that we've taken all the states which are light. Light states have some exponential growth when you take tau to I infinity. But if you remove all those, and you're just left with things which decay exponentially at the cusp, then you have a square integrable function on the fundamental domain of SL2Z. So Z spec is such a function. And by the spectral theorem, it admits a unique decomposition into a complete SL2Z invariant eigenbasis of the Laplacian on the upper half plane. There are 3 pieces to this decomposition. I'm not giving you the details because we won't need them, but there's a constant term. That's not really important for today, although for other applications it is. There's a continuous branch and there's a discrete branch. Okay. So the continuous branch are given by non-holomorphic Eisenstein series on the critical line, with index S equals 1/2 plus I times real. Eisenstein series obey this Laplace equation. And there's an infinite set of discrete eigenfunctions, known as Moss cusp forms, labeled by some spectral parameter, omega n. So they're discretely spaced, but it's known there's an infinite number of them, and the number of them grows linearly at large spectral parameter, quadratically, I should say. These are nicely sort of reviewed from a physicist's point of view, and some nice calculations actually done in this other paper, which also studies the kind of questions I'm talking about today from a slightly different point of view. So I'd recommend those papers as well. So there's a lot one could say here, but I really just want to jump to the point for what we need. Based on what I said previously, this appears a bit of a non sequitur. What does it have to do with periodic orbits? Well, the point is to go to the density of states. So just take this formula and perform the inverse Laplace transform to extract the corresponding density of states rho spec. And we ask, how do these basis eigenfunctions look when you think of them as basis densities? So the spectral density decomposes like this. There's the continuous piece and the discrete piece. And it turns out that a given eigenbasis element just looks exactly like a periodic orbit. So you take these, say the Eisenstein series, you do this integral transform to get the corresponding basis density basis element, and it can be written exactly in this form with this identification of an action, a period, which indeed is the derivative of this, and a determinant piece. This little a is a Fourier coefficient of spin j of the Eisenstein series. The explicit form is not important, right? So here I'm looking at some fixed spin j component of this thing. So it turns out the spectral decomposition of this density has exactly the form of a Gutzwiller trace formula. These identifications are smooth in spin. If you take j to 0, you get the actual result you get by doing the transform for the j equals 0 component. And this action is real. There are different choices one can make, and exactly how to identify which piece of the full answer for this with which piece of this is actually, there's some choice there. And that's actually something we're realizing. There are some better choices that one can make. I won't talk about that here. But the point is that the full thing clearly is of the form of a period or an orbit a la Gutzwiller. So to summarize, we have this trace formula for CFT2 states, this heavy part of the spectrum plus the modular completion of the light stuff. It expands the spectral density in a modular invariant set of periodic orbits. And what's interesting about this is that these orbits are defined with respect to the same operator, that is the hyperbolic Laplacian, for any CFT. The theory-dependent part is not the set of orbits, but the overlaps here. So in other words, every 2D CFT is modular invariant, and that actually yields a universal set of periodic orbits over which we can expand this part of the density of states, where the theory dependence just comes in the different weights of the orbits. So now we have a path to establishing random matrix universality in 2D CFTs. We just do what people do with Gutzwiller in the quantum system realm. First, we want to take a square. We want to find an analog of the so-called Berry's diagonal approximation to the spectral form factor, and then we go to we take this approximation, and then we extract the condition on these overlaps for the existence of a linear ramp in the spectral form factor, which is one widely used diagnostic of random matrix universality. So first, we find the diagonal approximation, right? And just to be clear, in what follows, I'm taking a, let's say, phenomenological approach to constructing what the diagonal approximation means in 2D CFT. In particular, I'm not explaining at what time scale this behavior is onset as a function of CFT parameters. I'm just giving a dictionary for what the diagonal approximation means in the context of this trace formula. Now, what it means is fairly obvious at this point, because in Berry's diagonal approximation, you take a product of a sum of her periodic orbits, And you identify, so you have a double sum, and you identify those orbits with equal and opposite actions. And that collapses the double sum to a single sum. So now we have a sum over orbits here. The orbits are given by the eigenbasis elements. So we should just go to the diagonal in eigenspace. That is, we should pair these SL2Z eigenfunctions. And so that's what I've written here. If you took a product of two Z's, each with their own expansion, you'd have a lot of cross terms and double integrals, but this is the sort of isolation onto the diagonal of that product. You might ask, why did I call this Z Hecke? I'm going to sort of skip some of this detail now. The point is that you want to explain how you get this by starting with a factorized product of two of these Z specs. And you can go from a factorized product to this non-factorized diagonal approximation by doing a certain projection onto the kernel of an operator made from the difference of two Hecke operators. Hecke operators are things which, when they act on eigenbasis elements, they spit out Fourier coefficients. And so if I act on some product of eigenbasis elements with the difference of Hecke operators, this spits out the difference of Fourier coefficients. And so the kernel of that identifies the eigenfunctions with each other. Okay. So now that we've done the first step, let's extract the condition for the emergence of a linear ramp. That is the random matrix universality condition for 2D CFTs. This is sort of the mildest form. We're not insisting that there's some full signed kernel we're reproducing. We're just reproducing the ramp. Okay. That's what the diagonal approximation does for a living. So for simplicity, let us look at the scalar-scalar component of the Fourier decomposition. So we have a product of partition functions, of chaotic partition functions, Z spec. Each of them can be decomposed in spin, in the 2D CFT sense, Lorentz spin. So we look at the scalar-scalar component, it's the simplest. And we go to low temperature by taking im tau 1 and im tau 2, that is y1 and y2, to infinity, and we hold the ratio fixed. You can show that this diagonal thing is linear in R times some function root z times R of z. This is given explicitly just as the inverse Mellin transform of this squared overlap. So it's just some processing of this squared overlap piece. And z is this ratio which one tunes. For example, to go to late times in the spectral form factor, you take z to -1, because we take y1 to it, y2 to minus it, and we take t large, right? So R of z is the thing which controls the 0, 0 component of this diagonal projection. And to make a slightly long story short, insisting on a linear ramp means when you take z to -1, this thing must have a simple pole. But this thing is just the inverse Mellin transform of this squared overlap. And so this is really a condition on the squared overlap. What is that condition? It's that as you go to large spectral parameter, that is, as you go to infinity in spectral space, the squared overlap decays exponentially with a coefficient given by a constant, which determines the RMT ensemble of interest. So this is the slope of the ramp. CRMT is 1 for GUE, 2 for GOE, etc. So this is a microscopic condition on the spectrum of a 2D CFT, which allows you to determine whether its spectral form factor, defined as this product of two Z specs, has a ramp or not. So let me summarize this in a cartoon. We start with our partition function. We isolate the chaotic part in an SL2Z invariant way that lands us on this Z spec. So that's the first non-trivial point. This is the definition of the chaotic spectrum of a 2D CFT that I want to propose. Now that you have that, you square it and you take the diagonal approximation, and you go to late times and insist on the presence of a ramp. And that leads you to this condition here. This is phrased microscopically, right? Z spec is something that exists in an individual 2D CFT. And to derive this, one needs to do some sort of smoothing, which ends up implementing the diagonal approximation for you. But given the presence of that approximation, then one can derive this condition. Okay, so let me make some comments. The first is a philosophical comment. The modular invariance seems to know about the fine structure of the chaotic spectrum. By fine structure, I mean the presence of some random matrix signature. Modular invariance was crucial for arriving at this trace formula. You can think of the trace formula as telling us that, right, so it's a sum over periodic orbits. This is some sort of signature of a classically chaotic system, and then we use those to extract this random matrix universal behavior. C minus 1 over 12 seems to have a sharp physical meaning, even at finite C. Why? Because that's the cutoff for between light and heavy states in the sense of this spectral decomposition. Right. There it operates as the threshold for square integrability, but what's nice about this is that at large central charge, C minus 1 over 12 is the semi-classical threshold for BTZ black holes in AdS3 gravity. But even at finite C, it seems to play an important role in telling us where we should start thinking about the chaotic part of the spectrum. And building on that, and now transitioning to some ideas in progress, we can address a pervasive lore in the field. So something that you sometimes hear and we sort of believe is that generic irrational CFTs are chaotic. Now, that statement was kind of fuzzy because, well, what does it mean for the CFT to be chaotic? Or what does generic mean? Is this not tautological? Absent an independent definition, it becomes so. But now we're in a position to formulate and perhaps prove a version of this statement. One can formulate it in the following way. If we impose unitarity, compactness, C greater than 1, and a twist gap, that is, no extra currents beyond those of Virasoro, and some gap in the twists of non-vacuum primaries. And if we forbid this ramp condition that I showed you previously, are there any solutions of the bootstrap? And if the answer is no, then every CFT obeying this list of properties is a CFT that obeys random matrix universality in the sense of having a linear ramp in its coarse-grained spectral form factor. So let me formulate this slightly differently. In quantum chaos, there's a widely held conjecture that links classical chaos to random matrix theory. This is this famous BGS conjecture, which, roughly speaking, is the statement that energy levels of classically chaotic systems obey statistics of a random matrix ensemble. So if we define generic CFTs as those obeying this list of properties, that's just a definition, right? Then one can formulate a BGS for CFT conjecture, if you like, which is that all generic CFTs obey the ramp condition. That is, you take any CFT obeying these conditions, you subtract off the light stuff and their modular completion, you're left with an explicit function, Z spec, and you check whether it obeys this condition. The conjecture is that it always does. That would be the analog of BGS for 2D CFTs in the framework of this trace formula. Now, there's a stronger form that one can formulate, but at this point it's vaguer, so I'm just mentioning it, but I don't really know what I think of it, which is that not only do all generic CFTs obey the ramp condition, but they exhibit full random matrix statistics, right? So in other words, they exhibit some suitable 2D CFT avatar of random matrix statistics that upgrades the full sign kernel to something which lives in 2D CFT compatible with Virasoro and SL2Z and so on. I don't know exactly what the form of that last 2D CFT upgrade of random matrix theory per se is, but that's really the fuller thing that one might suspect is true if you're just generalizing BGS. Okay.
Go ahead, Salir.
So what about Narayan CFTs? I mean, they're not chaotic, right? Or
Right.
at random,
Right.
but so that's an exception to your conjecture here. Is that right?
No, so they would have a zero twist gap because they have extra currents.
Oh, I see. That's what. Okay, thank you.
Yeah. So really, what I mean to what I'm trying to say is just look at a CFT whose maximal chiral algebra is Virasoro, and if C is greater than 1, then and then base unitarity and compactness. This is like a nice typical what we'd call a rational CFT. An arraign would have all these extra U1 to the C currents. So for that case, you should really one should identify the maximal chiral algebra and formulate any statements with respect to that. And if you do that, then the arraign they're always living right on the edge of irrationality. So I would never say that. I would say those are not chaotic in the sense that I'm trying to get at here, even for the U1 to the C version of this statement. You can check for an arraign whether it obeys the ramp condition, and it does not.
Okay, thanks.
Sure. Actually, let me say another thing along those lines. So there's another piece of circumstantial evidence for this conjecture. Say you take a rational CFT and you want to ask about its Z spec and whether it obeys the condition and so on. So the claim is that, suitably understood, Z spec for a rational CFT should not, you would not expect that to exhibit the ramp condition. Right? That doesn't follow from this, but it's morally what a good definition should obey that. But actually, more is true. In a rational CFT, Z spec vanishes identically. To be a little more precise, in a rational CFT, you shouldn't form Z spec from the Virasoro primary partition function because it's rational. So that thing where you multiply by root im tau eta squared, that's not a positive state sum. Instead, just work with the full partition function Z, sum over all states. You're not losing anything, but there's no such thing as a modular invariant primary partition function for a rational CFT because it would just be a finite Q sum. It's never modular invariant. So just work with Z itself and then go through this whole thing. Z spec actually vanishes identically. So that's nice circumstantial evidence for this in the sense that not only is the object that is supposed to exhibit chaos for irrational CFTs, but not for rational CFTs, not only does it not exhibit chaos for rational CFTs, it just vanishes. So I find this to be nice. Okay. Good. So looks like I have 10 or 15 minutes. Is that right?
Yeah, I think you have 15 minutes.
Okay, good. Are there any other questions before we sort of shift to the gravity side? Okay.
I have a question.
Yes.
Like when you are doing the torus partition function, don't you expect higher loop corrections to it?
Loops in what?
On the world sheet, or rather, I mean, not world sheet, that would be string theory, but I mean in the sense that the torus is a one loop thing. So I mean,
but not well. I'm thinking of it just as some fixed topology on which I can put my theory once and for all, and then study it. And in particular, if I want to access the spectrum of local operators, then that is the relevant topology for the state operator correspondence.
Is there a small parameter that kind of excludes those higher loop corrections?
No, but I think you shouldn't think of them as higher loop corrections. They're just different choices of fixed manifolds in which to put your CFT. And if you go to some higher genus topology, then the partition function on that topology contains more data than just the spectrum. It contains products of OP coefficients and so on. So there's no small parameter. There's just a choice being made. Yeah. And it's the choice that one wants to study the spectrum of local operators.
Okay.
Okay. So now back into the bulk. And some of this spectral technology will really pay off. Okay. So let me first define what I will mean by wormhole for the talk. So we recall a familiar feature of AdS3 holography, which you might think back to this black hole fairy tale, which is that in the bulk, you have a semi-classical gravity theory, which is invariant under large diffeomorphisms that act at infinity, right? So they act non-trivially at infinity, and that non-trivial action is sort of implemented in the bulk by a sum over geometries, and in particular, boundary modular invariance is implemented as a sum over bulk geometries. Right? A modular transformation on the boundary is some large diffeomorphism, and you sum over all of them, and you get something which is invariant under all the necessary bulk and boundary symmetries. But the sum over geometries is what's geometrizing that boundary symmetry. That's a statement about semi-classical gravity, to be clear. So this motivates, in any case, a working geometric definition of a torus wormhole amplitude. We take a modular sum over some seed. So we have two boundary tori with modular parameters tau1 and tau2, and what we'll call a wormhole, and the corresponding wormhole amplitude, z wormhole of tau1 and tau2, is some sum over relative modular transformations of the two tori of some seed function, f naught, which is invariant already under simultaneous modular transformations. So altogether, this thing is invariant under independent transformations of tau1 and tau2. And this is what we'll call Z wormhole. Okay. Actually, in order to prove the statement I'm about to show you, you want this seed to be invariant not just under simultaneous SL2Z transformations, but actually SL2R transformations. That's a technical point. I feel I have to say that. But given that, one can prove the following statement. This wormhole amplitude takes exactly the form of one of these Hecke partition functions. That is, it admits a double spectral decomposition into a diagonal projection of eigenfunctions with some overlap F wormhole of S, which is determined in turn by the seed in some definite way by some integral transformation. And so we see, for example, that the entire amplitude is fixed by the Eisenstein overlaps, right? These cusp form pieces, it's the same function. So once you know this, and you know this, for any wormhole obeying this form. And recall that this in turn is fixed by the scalar Fourier mode at low temperature, which in turn is fixed by this R of Z thing. That was this thing which has a pole as Z goes to -1, which is the linear ramp if you go to Lorentzian variables. Okay, so wormholes defined in this geometric way are very constrained from the spectral point of view. So in other words, the SL2Z spectral basis diagonalizes correlations. And wormholes, as we've been taught in one lower dimension, geometrize the diagonal approximation. So if you put these two things together, it leads us to propose what we call the wormhole fairy tale, which is that if you want to interpret a wormhole amplitude microscopically, you should identify this overlap with the square of the overlap of a CFT partition function Z spec with the Eisenstein series, right? In other words, identify Z wormhole with some Z Hecke, this diagonal projection of squared chaotic partition functions. Okay, so now we have this point of view about how wormholes geometrize the diagonal approximation and how on the boundary side, the SL2Z spectral basis is the right basis for diagonalizing these chaotic correlations. And now we want to turn to the Cotler-Jensen case. Okay, good. So the Cotler-Jensen wormhole is exactly of this form, no coincidence. And the seed is very simple. It's just 1 over the chordal distance on the hyperbolic space between 2 points, tau1 and tau2. So they did a calculation. This was the output of their calculation. Again, it's not a saddle point. And interestingly, it's independent of G Newton. That is, it's independent of central charge. This was always sort of slightly mysterious. It's compatible with the fact that it's not a saddle point. So there's no e to the minus c times action plus order 1 plus dot, dot, dot. The whole thing is just order 1 in units of central charge. We'll return to that in a bit. But now we have this explicit wormhole. So we just plug it into our formulas. In spectral space, it looks like this. So the Cotler-Jensen wormhole is equal to the following diagonal projection, where the overlaps are very simple. They're just products of gamma. Right? This is like 1 over sine. Right? If you go to temperature space, then this function R of z, which controls the scalar Fourier mode of this, is literally equal to 1 over pi times 1 over 1 plus c. This is exactly the ramp. Right? The ramp was a simple pole in R of z at z goes to minus 1. Here, that's the full answer, not just asymptotically in some z goes to minus 1 limit, not just asymptotically at late times. For this reason, you should think of the Cotler-Jensen wormhole as extremal. We've processed all the symmetries, the SL2Z symmetry, the Virasoro symmetry, and the resulting function, which determines, and the wormhole symmetry. The whole thing's determined by this function R of z, so that's the remaining freedom we have left. And the Cotler-Jensen answer for pure gravity sets this function exactly equal to the double-scaled RMT result. So this is something we call max RMT, because this gives the maximal realization of random matrix universality encoded in the ramp, consistent with the symmetries of the problem. One can say that the BTZ microstate spectrum is, quote unquote, as random as possible in the sense of staying as close as possible to RMT statistics. There are corrections, but they're due solely to Virasoro and SL2Z alone. Right? The corrections come from plugging this into this. And so if you expand, so tau1 and tau2, these are functions of time and temperature. If you expand at late times, there are corrections to the ramp, but those come purely from the modular invariance of the problem. Right? This is similar to the sort of statement of BGS in a given, classically chaotic system. It always obeys random matrix universality, regardless of the sort of underlying dynamics. Here, some vague analogy with that, we have this extremal solution, and there are deviations from the pure random matrix theory of behavior, but those are just due to the symmetries alone, not the dynamics. Okay, so the wormhole is kind of on the boundary of all possible wormhole amplitudes as far as random matrix theory is concerned. And so you can also put it slightly differently, slightly fancifully. Pure gravity is maximally chaotic, not just at early times, but also at late times. At early times, it's known to saturate this bound-on chaos, which is diagnostic of the out-of-time order correlators. At late times, where you sort of enter the random matrix regime, pure gravity spectrum seems to give the random matrix theory answer exactly to the extent possible. Now, returning to this slide for a second, on this third point, we can sort of explain why this is true from a different point of view. The ramp is independent of central charge because the slope is just an order 1 number fixed by the RMT ensemble. But as we explained before, the ramp fixes an entire wormhole amplitude because of the strong symmetries of wormhole amplitudes. So the whole thing is C independent. Okay, so a few comments and then transitioning to the sort of factorization piece, and then I'll conclude. The Cotler-Jensen wormhole admits a microscopic CFT2 interpretation. We're able to take that amplitude, write it in a language where the spectral correlations are diagonalized, and then think of it as this diagonal projection of 2 copies of a single underlying CFT partition function. This is in some sense a realization of this apparent averaging idea emphasized by Schlenker and Witten. In view of time, I won't linger too much on this, but basically the idea was that you have some infinite sequence of CFTs with a large C limit. That's the limit in which semi-classical gravity and AdS3 emerges. But there are differences between the actual discrete sequence and the smooth large C approximation to it. This difference ends up being responsible for some randomness in the black hole microstates. And what semi-classical gravity is computing are their moments. So the Cotler-Jensen wormhole is sort of the most ensemble-y looking thing that people tend to talk about in AdS3 gravity, but it can be given an emergent, a microscopic interpretation in which the apparent averaging emerges dynamically from some underlying chaotic dynamics of a microscopic CFT, a large central charge. Okay, in the remaining few minutes, let's talk about how we can factorize this thing and why. So we have this Cotler-Jensen amplitude, right? So here I'm writing in slightly different language. This is basically the same formula as before. E star and E are related by some zeta function prefactor. This is called the completed Eisenstein series usually. That's okay. But the point is that because we're expanding in this universal eigenbasis of SL2Z invariant eigenfunctions, each of which corresponds to a periodic orbit, we can actually factorize the wormhole, right, by identifying these overlaps with the square of the overlaps of some underlying CFT. So that gives us the actual Z spec, which here I've called Z RMT, that forms 1/2 of the wormhole, if you like. So this function here, this was the gamma gamma from before, that's just the square of the overlap of some function Z RMT, which corrects the naive gravity spectrum. In other words, the partition function of semi-classical gravity should be viewed as the sum of the MWK piece summing over the smooth bulk saddles, and a new piece called ZRMT, which encodes the leading RMT fluctuations of the black hole spectrum. So in our general language from before, this is Z hat light. It's the modular completion of the vacuum module. And this is the leading order piece of Z spec for pure gravity, such that when you square it and project it, you get the Cotler-Jensen wormhole. So we are extracting this piece from the wormhole. As a result, there's actually some sign ambiguities, right? So the overlap squared equals this thing. And likewise for these. But the signs are not fixed by this calculation because we're factorizing some quadratic thing. It'd be nice to be able to fix these signs. But regardless, it's intriguing that the overlap is sign definite on the critical line, because right, this is some inner product with the Ley-Peterson measure, and neither of these functions is independently sign definite on the fundamental domain. For example, the Eisenstein series, when averaged over the fundamental domain, vanishes. So the fact that it's sign definite is nice, and it suggests a possible bootstrap constraint at large C, which is that this overlap perhaps is always positive definite for all frequencies omega on the critical line. We haven't pursued that much, but I think it's an interesting direction. So how to find the random matrices in a 2D CFT dual to AdS3 pure gravity. Here's the cartoon from before. We identify Z Hecke with Z Cotler-Jensen, and then we factorize by extracting this integrand and taking the square root. So we're nearly done. We're not nearly done with the pure gravity problem, though, because the Cotler-Jensen wormhole is not fully non-perturbative. It's expected to be the leading topology in some infinite series where you have some space-time in the bulk connecting two asymptotic torus boundaries, where in the bulk there is some higher topology stuff happening. And it's expected that in some rough analogy to the case in JT-RMT, that these are suppressed exponentially in the central charge. So for which there's some evidence from this matrix tensor model picture of Bellin, DeBoer et al. So we don't have a complete proposal for these random matrix theory pieces that one's supposed to add to the sum of our saddles. We've just determined the leading piece. So here's some picture of what I said. There's some other topologies which would generate wormholes, which would necessarily be off-shell. And one would have to do some computation and ask how they affect the torus partition function by doing this kind of factorization game. So we've determined this piece here, but this is just some placeholder for whatever other higher non-perturbative effects there are. Let me emphasize that this must be non-zero, actually, because if we ask, is the sum of recitals plus this ZRMT unitary yet? The answer is no. Recall this is independent of C, whereas the non-unitarity here depends on C, so there was no chance of that. There's going to be some infinite series of corrections here. And by the same logic, you can actually prove that the black hole threshold is strictly below C minus 1 over 12. Because if it weren't, then there wouldn't be an order of limits issue. We could take large C, cross this off, and we should still get something unitary. But we can't, so there's some sort of order of limits between large C and going near the threshold, which is compatible with this proposal here. That's a small comment. But let me now conclude. So we have this picture for chaotic dynamics and random matrix statistics of 2D CFTs. There are lots of things to do. We're currently trying to understand more robustly how to go beyond the ramp in 2D CFT, how to go beyond the diagonal, to phrase better, more systematically, how you correct the diagonal approximation in some sort of CFT analog of encounter theory in the theory of periodic orbits. More generally, we'd like to understand how to incorporate these random matrix statistics into bootstrap approaches so as to try to prove or take some steps toward proving this BGS for CFT conjecture. In the bulk, there's of course lots to do. You could try to compute directly certain off-shell geometries with either 1 or 2 asymptotic boundaries. And so let me just pause here. Thanks.
Yeah, let's thank Eric for a wonderful talk. Yeah, Somnath, please go ahead. Ask your question.
Yeah, so I was just wondering what implications does all this have for, say, the computation of the black hole entropy? Because, the black hole entropy calculations depend on the semi-classical partition function, right? So now that would be, in general, be covered by the ZMWK. Now, if you add something else to it, wouldn't that change?
Yes, it would. But when you say it's covered by ZMWK, that's just the leading order semi-classical, say, Bekenstein-Hawking entropy plus, plus some corrections. And there are regimes where, in this near extremal large spin regime, where that would-be entropy is horribly unphysical. So we know one must correct it with something.
Yeah, but are there any calculations which derive those computations so that you can check whether your answer gives something similar to that?
When you say, I'm not sure what you mean something similar.
If there are calculations which compute the corrections, as you said, is there any way you can get it from the ZRMT here for the Z?
Yeah, I'd say ZRMT is furnishing a correction to black hole entropy. It is a new piece of the density of states, and it's much smaller than the Cardy piece, exponentially smaller, right? Loosely speaking, we should think of Cardy as Cardy's exponential growth of states at large delta, but ZRMT, indeed Z-spec in general, will not have an exponential growth at large delta because you've subtracted all that stuff out. That's sitting in the modular completion of the vacuum and the other light states, right? So ZRMT is much smaller. It's these fluctuations, but it is a correction. It is an explicit correction.
Is there any way to independently check it, whether the answer you're getting is correct or not?
Yeah, right. That's a good question. And that's kind of what this first bullet point is. So the claim is that there should be some set of 3 manifolds in the bulk with a single torus boundary, which are off shell, but whose contributions to the path integral, when summed over, reproduce ZRMT. Now, what exactly the rules are there is, I don't know. We don't really know how or which off-shell topologies to include, but we just know we need to figure that out. There's some progress on this, and I have some work in progress with Boris Post, a student in Amsterdam, to derive some off-shell contributions, but we don't yet know what set of topologies we're supposed to sum over to get this ZRMT.
Okay.
Just one more comment. In Maxfield and Toriatri's paper, they do this sort of JT with defects calculation, and they say in AdS3 we should sum over Seifert manifolds. These are smooth off-shell solutions, smooth off-shell geometries rather, and we claim that if you sum over Seifert manifold contributions to the AdS3 path integral, you will reproduce our calculation that corrects a near extremal negativity. But no one has been able to do that. But that's one precedent in the literature for a proposal like this.
Subhi, please ask your question.
So when you say ZRMT, do you think it's just a matrix ensemble like happens for JT gravity, just a single matrix, or it's some more general object?
Yeah, that's a good question. I mean, for now, it's just an explicit or almost explicit function, right? So we know it in the spectral decomposition, right? Here, the square of its overlaps. Up to the signs issue, ZRMT is just, it just admits a spectral decomposition with these as the overlaps. So we know it as a function up to signs, but how we're supposed to think of it, is there some kind of actual 2D CFT version of a random matrix underneath? We're trying to figure that out now by going beyond the diagonal and asking like how can we upgrade, say, the full area model to 2D CFT? In other words, putting it in the context of this spectral language. We're trying to understand that, and hopefully we can then address your question, but I don't know the answer yet. In other words, like here I'm saying that ZRMT is a microscopic CFT quantity, but it could also be that it's the leading approximation to something you get by studying a suitable CFT2 avatar of a random matrix ensemble with some spectral density. That would kind of unify the sort of microscopic and, averaged pictures.
Takehiro Izuma, please ask your question.
Yes, I'm Takehiro Azuma, and I have a very nice question. So there are scenarios in which the matrix model describes string theory, such as one matrix model describing the non-critical strings. And I wonder whether your scenario is related to the correspondence between the one matrix model and the string theory.
Not that I know of.
Oh.
Not that I know of. Yeah, the closest connection to string theory might be through this so-called Virasoro minimal string matrix model, where loosely speaking, I think that they wrote down a matrix model with a given spectral density, which is supposed to capture the near extremal random matrix statistics of 2D CFTs, and it has some string interpretation. But what that picture has to do with what I've said today, I don't see any direct relation, but it could be that sort of Virasoro minimal string matrix model is something that, I think that the point is that emerges, like if you take any 2D CFT and go to this large spin near extremal regime, that matrix model is governing the dynamics. But how to phrase that in today's language, I don't.
Thank you very much.
Sure.
Are there any more questions? If not, then let's thank Eric once again for a wonderful talk. Thanks, Ajit.
Thank you. This was fun.
And thank you very much.
All right. Thanks.
Bye-bye. Yeah.